Alright, good afternoon. It is a small class today. We've been running about 50% most of the quarter so far, which is shockingly small, but this is 25%. But that's okay. Alright, let's start by talking about the homework that I just graded. And then we'll talk about the new homework that was posted. And then we'll keep talking about proofs. So, homework 2. Alright, so homework 2, I looked at, I glanced at all the questions, but I graded 1.5, questions 2, B, C, and D, and then question 10, A, and B. And let me bring up the homework assignment. So a big issue people had was not seeing or not following these instructions in Canvas. So when I post homework, I usually try to put clarifications or things like that if they're needed. So for example, 1.5, 2, 4, 10, number 2 for A, C, and D, there are 4 questions, right? So these questions asked you to do something for n equals 1, 2, 3, and 4. And some people did one summation where they added up the sums for n equals 1, 2, 3, and 4. And you're supposed to have 4 different answers in here. So there were, those kinds of misunderstandings. But if you did the correct question, most people seem to get these summations right. They have the idea math errors all over the place, which I'm not too worried about, but they do affect the answer, so double check your math work. Question 10 was doing a product. So just as we have, a sum from I equals 0 to 5, we can do this product I equals 0 to 5. And this means, take a bunch of things and multiply them together. Whereas this means take a bunch of things and add them. And about 20% of the class for this question 1.510a, they wrote out the product. They said this would be 1 times 2 times 4 times 8, and then they wrote down the sum of those instead of the product. And I don't know if that's just a common glitch or what, but yeah, so I don't know. But I mean, people wrote down 1 times 2 times 4 times 8, and then they said equals, and they wrote down 15. So that was kind of interesting. But yeah, so this pi symbol is a product, and it's a multiplication. The part B of that was this product, k over k plus 1 from k equals 1 to 100, I believe. And my note on there said it's relatively straightforward. Think about it and try not to do too much work. So write out the first few terms. This is 1 over 2 times 2 over 3 times 3 over 4 times 99 over 100 times 100 over 101. And my inner monkey gets excited when it sees problems like this, because it thinks, oh, I can do this without having to actually do a lot of work, because I can cancel things, right? I love this when I was in grade school, being able to cancel numerator and denominator. So bang, 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 bang. All you're left with is 1 over 101. And a lot of times in this course, we're looking for formulas, perhaps, or expressions like this rather than numbers. So you can put this into a calculator and start cranking out a product of these things, and you can see that it's heading towards zero. But if you analyze this expression, you can see this cool little thing that you can do. You could also write this out as 100 factorial over 101 factorial, if you know and like factorials. But that's a big, huge number. That's a big, huge number. 101 times bigger than that big, huge number, right? And that's a little unwieldy to work with. Whereas this is just like nice and elegant. Yeah, it should converge to zero as the upper bound goes to infinity. But I don't know. No, I didn't actually try that. Yeah, no, I didn't run the series. Honestly, it's been way too many years since I did calculus. Yeah, canceling is fun. We're going to do that a lot when we get to the unit on counting and we do probability. We'll lop off things from numerator and denominator. Because you're really, writing this as 1 times 2 times 3. And the bottom is 2 times 3 times. Alright, that's the fraction we have. And multiplication is commutative, so that inspires us to take those out. Oh, I put the wrong thing on the bottom. Yeah, 101 should be on the bottom. Alright, cool. Let's see. So what else did I look at? Question 3.1, or section 3.1, question 2. So this was asking us to break compound propositions into simpler propositions. So for the following, identify simple propositions, express the compound in symbolic form, determine whether it's true or false. So the world is flat or 0 is an even integer. So this is one proposition, the world is flat. Let's call that P. This is another proposition, 0 is an even integer. Let's call that Q. So this statement is P or Q. And it turns out to be true. So a few things to note here. First of all, 0 is an even integer, right? Make that a subject heading. It's an integer, right, because it's a whole number. It's even because it's divisible by 2. What do you get if you divide 0 by 2? You get 0, which is an integer. So that one isn't obvious, but yeah, 0 is even. 0 is not odd, right? An odd number you divide by 2, you have a leftover. And 0 is evenly divisible. So that's one thing. Next thing, I want you to be very, very formal in how you write propositions. So don't say P equals 0 is an even integer. All right, don't write something like this. Where am I here? Don't say P equals 0 is an even integer, okay? Or Q equals 432, 802 is a multiple of 4. Okay, this is ambiguous. The equal sign means something very specific, particularly when we talk about mathematics. It means this has the value of the thing on the right. So is Q equal to the number 432,802, which is a multiple of 4, or is Q a proposition? Is it equal to this collection of words, right? And you know, maybe putting quotation marks around there helps a little, but just don't do this, okay? I didn't take off points for it. I will take off points for it in the future, though. Let P be the proposition. Zero is an even integer. Alright, I want you to state your propositions with that language. Let P be the proposition. Let Q be the proposition. R is the proposition. Something like that, but I'm not going to let you use the equal sign. Okay?
So, question about implications. For part B, would the implications of that be that either 432,802 is a multiple of 4, or that the other statement is false?
So digging into that problem, so it says if this thing is a multiple of 4, then this thing is even. So let P be the proposition, whatever that is, 432,802 is a multiple of 4. Let Q be the proposition, 432,802 is even. So that compound statement says if the first thing, then the second thing. So that's what that statement looks like in the language of propositional logic. It's an if-then. So the first thing implies the second thing. And then the exercise set asks us to determine whether this is true or false. Well, it turns out that, you know, P is false. And Q is true. But as long as P is false, this implication is true regardless of the value of Q. Because of that funny thing that implication does in its truth table, if false, then anything. I don't know if that addressed your question or not.
I still feel like I'm close to implications and understanding it, but it may not be applicable to this one. So implications are still a little fuzzy to me. Maybe you go to that after homework.
So the implication is saying, you know, if this is true, then that is true. It's a conditional statement.
Okay.
And so if this was true and that was false, then the implication would be false. The statement, if P then Q, would itself be false. But in any other case, the statement, if P then Q, turns out to be true.
Okay.
Cool. All right, so I looked at all the questions in that set. So 5 is a prime number, 6 is not divisible by 4. So if this is P and this is Q, P is true, Q is false, or Q is true, 6 is not divisible by 4. So this is a conjunction, P and Q, that's true. Part D, 3 is an integer and 3 is rational. 3 is both an integer and a rational. A rational is a fraction of 2 integers, and 3 can be written as 3 over 1. So that's a true and a true, that's true. Let's see, can you go over part C? Sure, so let P be the proposition that 5 is a prime number. 5 is prime, it's only divisible by 5 and 1, so that's true. Q is the proposition that 6 is not divisible by 4. That's also true. If you take 6 and divide by 4, it doesn't go in evenly. You get 1 with some stuff left over. Yeah, I forgot the word not the first time I did it a minute ago, too. Alright, and then for E, this says 2/3 is an integer and 2/3 is rational. That's false. That's true. So this is false, this is true. And so the conjunction is false. And then F, the sum of two even integers is even. That's a true statement. The sum of two odd integers is odd. That's a false statement. For example, 2 plus 2 is 4. Or 1 plus 1 is 2. That's the sum of two odds, but the sum is not odd. So this is a true and a false conjunction. That's false. And then section 3.2, truth tables. I looked at your truth tables for A, E, and F. And A is what we call a NAND gate in 250. And E is also a NAND gate, but written using De Morgan's law. And then F is just a OR gate of 4 inputs. So 16 rows. But I wanted to see if people actually wrote out all 16 rows, and they did. You did, so that's good. All right, so if you have questions about those, go ahead and ask. But it looked like no big surprises or issues there. All right, let's look at the next homework. So this is homework 3. This should be due a week from today, so February 1st. And these are questions from 3.4 and 3.5. And they're proof questions. And I've got a note here to pay attention to. The questions are written in the form, bunch of stuff separated by commas, and then this double arrow, and then some stuff on the right. Okay? You should take this as meaning, if all the stuff to the left of the arrow is true, then the thing on the right of the arrow is true. So if you look in the text, at 3.5, your questions look like this. Stuff, comma, stuff, comma, stuff implies stuff. So let's just write one of these out. So if P, then Q. If not R, then not Q.
You're blocking the.
I know. I'm copying the problem over. Think so. Not R implies not P. Alright, so just as an example, 3.5.4a says, prove this. Okay, so what is this saying? This is saying, if this, and this are true, then this is also true. If we wrote this in the form that we were writing proofs on Friday, it would look like this. If P, then Q. If not R, then not Q. Not R, therefore not P. This would be what you're being asked to prove. Okay? And that's really important. Because I've had students who take this as 3 conditional statements. If P, then Q. If not R, then not Q. If not R, then not P. And that's a totally different theorem. Right? So it's this, throw in parentheses if you like. This and this and this taken together gives you that. So your goal is to write a formal proof where these are your three hypotheses and this is your conclusion. And you prove your conclusion by starting with your hypotheses and arguing logically using the laws of logic on page 58 and 59 in the text, for example. What if one of them is false but the others are true? Then we have, this proof does not apply. This theorem does not apply. This theorem simply says if these things are true, then that's true. It makes no claims about what happens if, for example, this is false. So yeah, assume your hypotheses are true. Because our goal is to show if the hypotheses are true, then this conclusion is true. So you can think of it as a conjunction, and this is the other way that this is sometimes written, which is what I'm nodding to in my note on Canvas. Right? If this and this and this are all true, then not P is true. All right, so so 3.5 questions 2, 4, and 6. 3.4 question 2 is it's a warm-up. So show that the common fallacy is not a law of logic. So you can do this by finding particular propositions P and Q such that P implies Q and P is false, but not Q is not. P implies Q is true, not P is true, but it turns out not Q is false. So find me a counterexample, right? That's the easiest way to show that something is not true. Just find a counterexample. And make P and Q propositions for which, we all understand their truth value. We understand the truth value of if P, then Q, and so on. So, I don't know, you can make propositions about numbers, you can make propositions about facts that there's no dispute over, so stay away from flat earths and politics. But find a counterexample. Yeah, your propositions can be anything. Can you make propositions about CSE215? Sure. Yeah, it can be anything. The only reason I'm clarifying that is I've had some people write propositions like, let P be the proposition I like broccoli, let Q be the proposition I play trumpet. And I don't know if the student who wrote that likes broccoli or plays the trumpet. So it's really hard to see that this demonstrates, a counterexample. So make them stuff that like Cyberpunk 2077 is a great game, etc. Can't grade it if you don't know the answer. Alright, so I want to, I was thinking about getting my brother a copy of it actually, because he wasn't able to find it, but it's fun just for the Easter eggs. So we're going to talk about some examples of proofs, but let me talk about something else first. Let me talk about fallacies. And then we'll go ahead and we'll start working on some of the other questions from 3.5. Remember, the odd-numbered questions have solutions in the back, so you're free to work on those with one another and compare answers and so on and so forth. And you can use that to test and develop your understanding of these concepts. So I'll pick on those also in class in a few minutes to go through some examples of proofs. So I want to talk about fallacies. This is sort of the last conceptual piece of this part of the course. And then I want to go through some sample proofs from section 3.5. And then I want to talk about indirect proofs, go through a sample problem of that, and then go through some more sort of general proof type questions, ones that don't necessarily look like, like this kind of thing, but ones that start off as kind of word problems. And I want to see how we can use some of this machinery we're developing to work on those. Ending with a proof that the square root of 2 is not rational, that you can't write square root of 2 as a ratio of two integers. And that'll be a launching point into some discussion about number theory. But let me start off with fallacies. So we know about detachment, right? Given that P implies Q and P is true, we can safely conclude Q. That's detachment. We also know if P implies Q and Q is false, P must be false. That's indirect reasoning. I don't know if you can hear my new neighbors or not. They've got a stereo, and I think they didn't bother with like mid-range or tweeters. They just got the bass speakers, because all I ever hear coming from them is a beat, and it's pretty loud. This is at least an interesting beat today. All right, so these are two valid laws of logic, and they come from the textbook. So these pages that I mentioned the other day, 57 and 58, have detachment, indirect reasoning, other things like that. There's two other theorems that are related to these that turn out to be false. They're not actually theorems. They're statements that are incorrect. So the first one is, if P then Q, Q therefore P. So these are going to be called fallacies. I think there's only one L in fallacy. Alright, so those first two things are theorems. Alright, this is a fallacy. If P then Q, Q therefore P. This is called the fallacy of affirming the conclusion. And it's not logically correct. This could be true, this could be true, and this could be false. Okay, example, P is the proposition, I win the lottery. Q is the proposition, I teach class today. If I win the lottery, I teach class today. Well, that's a true statement. I'm teaching class today, therefore I won the lottery. Doesn't follow. This is trying to run the arrow in the opposite direction. If P then Q, well, Q is true, so P must be true. That doesn't work logically. Right? If it's Monday, then we have class. We have class, therefore it must be Monday. Could be Wednesday, could be Friday. So this is not a valid law of logic. It's not a theorem. It's called a fallacy, and it's the fallacy of affirming the conclusion. Alright, here's our other fallacy. If P, then Q, not P, therefore not Q. And this is called denying the hypothesis. right? Again, if it's Monday, we have class. It's not Monday, therefore we don't have class. That's not true. If it's Wednesday, we're going to have class also. But this is saying, if this is true, then Q is true. Hey, P is not true, so Q must be false. Not logically correct. And it took me about 3 years of teaching this course before I could remember what these things are called. So put them on your note sheet if you want. But this is a fallacy you get when you take the conclusion and say it's true. That's the affirming the conclusion. This is a fallacy you get when you take the hypothesis and say it's false. You deny the hypothesis. That's where it's named from, I believe. So for for conditional reasoning, I thought the third row of the truth table P is true. I don't know what truth table P is.
Yeah, so it has a truth table for conditional reasoning, and it says if P implies Q, and P is true and Q is false, the answer is false. So can't we derive something from that?
So there's your possibilities, and this only fails to be true if the hypothesis is true and the conclusion is false. Otherwise, it's always true. So you could do some 250 and write a sum of products for this if you want, and simplify it, and you're going to find out that this turns out to be not P or Q. So if P is false, or if Q is true, and those turn out to be the same truth table. So this is a demonstration of this equivalence, which is one of those things in our 2 pages of laws of logic.
But in indirect reasoning, it says if Q is false, P must be true. But based on this table, oh, yeah, okay. Now I get it.
You got it?
Yeah, I get it.
Okay, cool. All right, so we've got 2 main theorems and 2 fallacies, which are very similar to the theorems, but not logically correct. All right, so let's look at some of these proofs in the questions for section 3.5. So the idea of proofs is to prove that things are theorems, right? So a theorem is a thing that can be shown to be true. And a proof is that demonstration that it is true. And there's 2 main approaches we're going to take to doing proofs. And it's called a direct proof or an indirect proof. And I want to just talk about direct proofs first. So what's the idea of a direct proof? Start with what you know to be true. Well, when you're proving a theorem, all that you know are the hypotheses that you're given and the laws of logic that you have in your toolbox. And using just those things, you need to be able to show that the conclusion that you're after is also true. So you're going to start with what you know, you're going to argue until you get to what you're trying to show. And so let's play with some exercises. So we can prove with truth tables, right? And that's just kind of a mechanical process. But we're interested in actually like coming up with formal proofs. So let's look at let's see. Let's just look at part E over here. So this is 3.5. 3E. And let me write this down and then I'll switch to my camera. So we're told not Q, comma, if P then Q, comma, P or T implies T. Alright, so we're trying to prove this theorem. And it's good to kind of look at this and see if you have some ideas on how to possibly get here. And you know, we did one of these with the theorem about getting an email and sleeping in and waking up refreshed, right? But here we're just starting with something in, you know, propositional language with propositional variables and such. We're trying to prove T. Well, I only have one statement here which says P or T. That's the only thing here that mentions T at all. And P or T does not prove T. This says P is true or T is true. But if that's the only thing I have that mentions T, that makes me think, you know, maybe I can do something to prove P is false. And if I know P is false, then that's going to prove that T must be true. And so how can I prove P is false? Well, here's the only thing that mentions P. And it says if P is true, then Q. And so you work from there. Or, you know, sometimes you just look at the statements and you just think, you know, hey, I can use the chain rule here, or I could use De Morgan's law hit there. And you just sort of play around with it. So let me just write out an example of a proof. So statement 1, I'm just going to write down not Q. And that's a hypothesis. Statement 2, I'm going to write if P then Q. And that's also a hypothesis. So what could I write from here? And we've got these implications. So I'm trying to put something together here. Do we need P or T2, or are we not doing that one yet? I could put that down. Yeah, I'll go ahead and list that here. And if you don't believe that any of these are red herrings, you can go ahead and start off with all of your hypotheses listed. So how can I write something new? What's a statement I can derive from these using some of these laws of logic?
Indirect reasoning says if P implies Q and not Q, not P.
All right. So we can put 1 and 2 together, and we could say not Q implies not P. We got that in chat window also. All right. This reason for this is indirect reasoning applied to statements 2 and 1. So we've got a new statement here. If not Q, then not P. Sorry, this is just not P. Right? So P implies Q, Q is false, therefore P is false. So we've got a new proposition we've written down. We've said P is false. Well, we have this other...
Absorption?
Yeah, so absorption says P and P or Q is the same as P. Let's see. I don't know if absorption would get us there immediately. Because we have not P and we have P or Q. But let's write that out.
Sorry.
That's okay. So we know this is true because this is just statements 4 and 3. But we can distribute that and. This becomes not P and P, or not P and T. And that's distribution. Well, not P and P is false, and that's negation law.
Should that be false or? Yeah, I thought negation was a biconditional.
So it's saying that P and not P is equivalent to false. So I can replace P and not P with false.
Okay.
And then false ORed with something is the same as the something. That's the identity law. Here again, we need to do a commutative law, but I'm going to skip that, and I'm just going to use identity law and say not P and T. So that's the identity law. And then we need one more step to go from not P and T to T. And that is down here. So what's the last step?
Disjunctive rejection.
Close. So disjunctive addition says P implies P or Q. We want to go kind of the other way. We want to know that not P and T gives us T.
Conjunctive simplification.
Yeah. So not P and T gives us T. And that's conjunctive simplification.
So since conjunctive simplification doesn't have a not P, would we have to translate it to P? Or
It's really saying that, you know, anything ANDed with anything else gives us that first anything. And anything ANDed with anything else also gives us that second anything else. And the P and Q here are just placeholders, right? So I could have written this as, you know, A and B gives you B. And that's the form of the rule that I'm using to get that and turn it into that.
gotcha, so it's like a substitution.
Yeah, it's a substitution, exactly. So that gives me T, which is what I was asked to show. So that's a very formal proof, right? We skipped almost no steps, and we numbered all of our propositions, and we wrote a reason for each new proposition in terms of, stuff that we already knew was true. And there's another way we could have done this, and I'm okay with this, but I don't want you to get too relaxed. We've shown that not P is true. So at this point, we could have said P is logically equivalent to false, right? Because not P is true, so not P is not true. I'll show you the steps. Not P is logically equivalent to true, so if we double negate that, we get that that's equivalent to not true, and the double negation of P is P, and the negation of true is false. But once you see this, you know that not P is true. That tells you that P is false. And we could have plugged that into P or T, which is a hypothesis, and said, okay, so false or T must be true. And then we could go from there directly to T using one of these simplifications. P or 0 is P, so that's the identity law. So here again, a couple of steps to this. One is sort of finding the path from what you're trying to do to the conclusion, and then two is writing it up. And they're both important steps, and particularly in the beginning, the most challenging part is going to be finding the path. How do I, show that T is true just knowing these three things? And that's really getting in and working with, these identities and these laws of logic and so on, and getting familiar with them. And the more familiar you are with them, the more readily they'll come up in your mind when you're trying to do these proofs. But then there's a second level, which is, the formal presentation of the proof, and that's a really important part. And that's sort of, once you know how to get from A to B, the drawing of that map for somebody else to read is a super critical piece of that. Otherwise, a proof and nobody else can benefit from it, right, if you can't demonstrate it. So we want to work on both of those in here. All right, questions on that? All right, so that was an example of a direct proof. Direct proof, you start with what you know, you argue logically, and at some point you come up with the conclusion you were trying to show. There's another proof strategy we can take, which is called an indirect proof. And indirect proofs are funky. These are also sometimes referred to as a proof by contradiction. So here's the casual conversation version of what an indirect proof is. you want to prove some proposition P. You start off by assuming that P is false, and then you go on to show that if that's the case, something absurd happens. And since we believe that absurdities don't exist, then we must conclude that P was in fact actually true. Alright, so we're trying to show P, we're going to assume not P. And we're going to argue till we get to a contradiction. And then that will force us to conclude, hey, I guess P was actually true. So here's the idea. We want to prove some proposition P. Assume P is false, argue logically, and eventually come up with a proof that false is true. And that's a contradiction. And now we make the following statement. If P is false, we get something ridiculous. So P must actually be true. And this is basically what a proof by contradiction or an indirect proof will look like. You need to fill in the stuff in here that gets you to false equals true. Alright, we'll come back and see a different version of this and look at a different interpretation of this, but let's actually do this with something. So let's do that same problem that we just did, but with an indirect proof. Alright, so I want an indirect proof of this theorem. Alright, I'm going to start off with my hypotheses. So not Q, that's a hypothesis. If P, then Q, that's a hypothesis. P or T, that's a hypothesis. Alright, now I'm going to write down the negation of the conclusion. So the conclusion of this theorem is supposed to be T. I'm trying to prove T is true. But instead, I'm going to start a proof and I'm going to assume that T is false. And I'm going to show that something absurd happens as a result. Well, if not T is true, then T is false. Right? And the reason for this is the negation of true is false. I shouldn't be using T in both places, but you know, big T, little t. All right. Well, if T is false and I know that P or T is true, then I know that P must be true. And that's a combination of the fact that T is false, that's statement 5. The fact that P or T is true, that's statement 3. And the fact that when you OR with false, you get back the thing that you ORed with, so the identity law. Well, if P is true and P implies Q, that means Q is true. This is statement 6 put together with statement 2 and direct reasoning, so detachment. But we've reached a contradiction. Because we've stated that not Q is true, and we've just shown that Q is true. So right now I can say contradiction between statements 1 and statement 7. And I can say that because I don't have to do any work to see that this and this contradict each other. If you have to do any work, you got to add more steps to your proof. Alright, so this is an important point. Don't stop too soon. Don't make the person reading your proof have to do any work. Maybe at this point where I wrote P, I can see that there's a contradiction, right? Because I know that P is true, and I know that P implies Q, which means Q is true, but I've also shown Q is false. But I'm not allowed to say contradiction at this point, because nothing on here directly contradicts each other unless you do some work. In particular, you do this work of applying detachment to steps 2 and 6 to show Q. Don't skip that work, okay? Spell it out until you've got something that clearly contradicts Q and not Q. And that's obvious enough of a contradiction for me in this class to say, okay, at this point there's a contradiction between 1 and 7. But if you were doing this for, you know, a really picky judge in a court of propositional logic, and you really wanted to nail the point, you could do the following. And you could say, well, Q and not Q is true because of statements 1 and 7. And then I think we have some sort of law about Q ended with not Q being equal to false. So this lets us say false, and that's the negation law. And at this point, I clearly have a contradiction with no work because we've just shown false is true. And so we don't necessarily take it down to a step where we end up writing false, but that's basically the punchline of a proof by contradiction, is you prove false. And anytime you can show false is true, that's a contradiction. So at this point you could say contradiction, and I draw this symbol, just a sideways hash mark, that means contradiction. But you can spell out contradiction if you like. Once you reach a contradiction, then this thing up here, which was an assumption, must be wrong. So having reached that point, now we can say, therefore, that statement must be wrong, which means its negation must be true, which means T must be true. And that's your QED point. So yeah, you do get to do QED. I showed you pages of Principia where the first few hundred pages led up to something that would eventually prove 1 + 1 = 2. So no, we're not going to prove that. That's a hard thing to prove. But I'll give you references to it if you want. Alright, so that's the idea of a proof by contradiction. Let's go back to this. and think about what we're doing here. Basically, we had a bunch of hypotheses, which we started off by assuming, and then we threw in this other thing here, this negation of t. And what did we show? We showed if t is false, then we can prove false. So not t implies f. That's what an indirect proof is showing. It's showing that negating the hypothesis, the conclusion, implies false. We know that a statement is logically equivalent to its contrapositive. So if we have shown this, we have also shown the following. Negation of false implies the negation of t. Well, what's the negation of false? That's true. What's the negation of t? That's t. Once we've shown this, we've proven that true implies t. And we know true is true, and so we've proven t. So this is logically equivalent to t. So in a sense, an indirect proof of t is a direct proof that not t implies false. Don't worry if that doesn't make sense. It's just something to amuse the back of our brains. I think of it as this way, right? Assume the negation of the conclusion, argue to an absurdity, and then say, therefore, the conclusion must have actually been true. All right, why do we care about this? Because sometimes indirect proofs are easier than direct ones. Sometimes the other way around. Let me mention another thing here to keep in mind. So here was our direct proof of question E, right? And remember, direct proof, we assumed all the hypotheses were true, and then we argued until we got to the conclusion we were after. This was our indirect proof of the same theorem. We negated the conclusion, right? And we argued to an absurdity. Alright, this will cost you points on the homework if you do this, so don't do this. Suppose I ask you to give an indirect proof of this. Okay, here's something that people do sometimes. They start off, by stating the hypotheses, okay, and then they state, the negation of the conclusion, so that's good so far, and then they go ahead and they do a direct proof of T. And at the end of this, you say T contradicts not T. And therefore not T can't be true, and so T must be true. And that's not really an indirect proof. Technically it's an indirect proof, but really that's a direct proof of T. And then you're saying, so not T can't be true, so T must be true. Right? But it's not an indirect proof. It's a direct proof. And then you wrapped a little bit of see-through paper around the outside and said, this is an indirect proof, right? An indirect proof should look different from the direct proof. It should start with the negation of the conclusion, and it should use this inside the proof. All right, ask me about that if you're unsure, if you want, before you turn in your homework, you can show me your indirect proof and ask me about it. But don't do it Monday morning. Do it before then. All right. So why do we do indirect proofs? Because sometimes some questions just lend themselves more easily to an indirect proof. So let me give you an example. So given integers a, b, and n, if n is the product of a and b, then a is less than or equal to the square root of n, or b is less than or equal to the square root of n. And we'd like to prove this. And so a direct proof would say, okay, n equals a times b, and you know, maybe take the square root of n, and that would be equal to the square root of a times the square root of b. But how does that tell us how a relates to the square root of n, and so on and so forth? And a direct proof is kind of hard to figure out for this, but an indirect proof really just kind of falls out on its own. So let's do an indirect proof. Alright, so I'm just going to work over integers, so I'm not going to keep saying integers. So n equals a times b. That's a hypothesis. I'm going to negate the conclusion. Okay, I'm going to take the negation of a is less than or equal to square root n, or b is less than or equal to square root n. And I'm going to argue to an absurdity. All right, I'm going to use De Morgan's law here. And this is a case where De Morgan's comes into play in like real life. The negation of a or b is the negation of b ANDed with the negation of a. So we have the negation of a less than or equal to square root of n, and we have the negation of b less than or equal to square root of n. So that's De Morgan's theorem. The negation of a is less than or equal to square root of n is what? What's the negation of this? Negation is a is bigger than square root of n. And the negation of this is b is bigger than the square root of n. Now what's our reason for that? I could say someone told me in chat. No. So we gotta be a little careful here, right? We can take some liberties, but we don't want to abuse them. So I'm going to put something here, which is just properties of less than or equal and greater than. we would actually have to do a lot of work to show that if something is not less than this, it must be greater than that. We've got to define what less than means. We've got to define what equal means, right? But this really just comes out of properties of integers. And you'll see me use this a lot on proofs in class, properties of integers. But you gotta be a little careful, right? You could claim that this is true because that's a property of integers, right? But that's using that too loosely, right? But I will let you take as given that if, you know, a is not less than or equal to this, it must be greater than that. Just be aware that we are, you know, kind of using something that might normally need to be proven, but not in this course. So we know a is bigger than the square root of n, and b is bigger than the square root of n. I'm going to multiply a by b, and I'm going to multiply square root n by square root n. And I'm going to say a times b is bigger than square root n times square root n. Let me make these all positive just for simplicity. So if I have two numbers that are bigger than two other numbers and I multiply those, they end up being bigger than the product of those, right? And this is, you know, more properties of integers. It's something we learn in some class that these inequalities are preserved as long as you multiply by positive numbers. And then step 6, let's just combine the square roots. A times b is bigger than n. And that's just, you know, more math. Square root n times square root n is n. I'm not going to make you prove that, right? We know that's what square root means. So we've just shown that a times b is bigger than n, and that's a contradiction. Because we had previously stated in step 1 that a times b is equal to n. And again, something can't be bigger than n and also equal to n. That's properties of inequalities, right? Therefore, the negation of the conclusion must have been false. So therefore, a is less than or equal to square root of n, or b is less than or equal to square root of n. And that's what we were trying to show. So that's an indirect proof of that theorem. And a direct proof is fairly tricky. Let's see, how'd you get from step 4 to step 5? So if these are all positive numbers, then we have this fact about inequalities. If a is bigger than b and c is bigger than d, then a times c is bigger than b times d. So we have a gentler fact. If a is bigger than b, we can multiply both sides by a positive number and preserve the inequality. So if a is bigger than b, then a times c is bigger than b times c. And if c is bigger than then I cheated here. Yeah, if C is bigger than D, then B times C is bigger than B times D. And so A times C is bigger than B times C, and B times C is bigger than B times D. We can use the transitive property and conclude that A times C is bigger than B times D. So I skipped a bunch of steps on you there. But the sloppier version of that is if everything's positive, you can multiply these and multiply these and get something that still preserves the inequality. Cool. All right, other questions? Let me leave you with a couple of definitions that we'll use heavily for the next few classes. An integer n is said to be even if there exists an integer k such that n equals 2 times k. An integer m is odd if there exists an integer j such that m equals 2 times j plus 1. An integer blob, an integer m. In commoner terms, an even number is twice an integer. An odd number is twice an integer plus 1. So for example, the number 10 can be written as 2 times 5, where 5 is an integer. 10 is even. The number 0 can be written as 2 times 0. This is an integer, so 0 is even. The number 17 can be written as 2 times 8 plus 1, where this is an integer, 17 is odd. The number 1 can be written as 2 times 0 plus 1. This is an integer, 1 is odd. The number -1 can be written as 2 times -1 plus 1. This is an integer, -1 is odd. So we know what evens and odds are, right? But this is a formal way of defining what it means for an integer to be even or to be odd. If it's even, we can write it as twice an integer. In other words, there exists an integer, we're calling it k, such that n is equal to 2 times k. And if it's odd, there exists an integer j, such that m is twice j plus 1. I could have said there exists an integer j, such that m equals twice j minus 1. It's an equivalent definition. So we're going to use these definitions and do a series of proofs about numbers. For example, proving that the sum of two even numbers is even. But remember, the sum of two odds is not even, is not odd. The sum of two odds is actually even. We can prove that pretty easily. We can prove that the square of an even number is even. We can prove that the square of an odd number is odd. but we'll also prove some other things that are fairly difficult to prove directly, but that we'll see indirect proofs for coming up with validation of these facts. So we'll play around with evens and odds. We'll do some more proofs on Wednesday related to those. And that will pretty much do us for propositional logic part 1. And then we'll talk about number theory. And we'll spend about a week on that. And then we'll come back to propositional logic and we'll develop the theory of mathematical induction. And that's the heart of CSE215 and in many ways the heart of computer science. So we'll get to that in a couple of weeks. Alright, try to get started on your homework before Wednesday so you can ask questions in class on Wednesday, and then work on it some more and ask more questions on Friday. That's the ideal. Anyway, have a good afternoon, and I will see you next time. Thanks.